should work.
Great. So next we have Jonas Haferkamp from ITP Berlin, and he'll tell us about linear growth of quantum circuit complexity.
Thanks a lot. Also, thank you for having me, for inviting me. Yeah, as it was announced, I'm going to talk about growth of complexity in random quantum circuits, and a result that we proved recently. I was lucky enough to collaborate on this project with Philippe Feist, Naga Kutakonda, Jens Eisert, and Nicole Junger-Halpern, which is this beautiful group of people. And then you can find the project under this archive identifier, but of course you can also just Google the title. So the key concept in this talk, as the title already suggests, is going to be quantum complexity. And complexity in general is an extremely well-established subject and sort of a ubiquitous quantity. And this is not very surprising because in full generality, obviously everyone who's interested in any kind of operation usually wants to know whether the implementation of this operation is going to be easy or whether it's going to be hard. So it's not surprising that the classical analog of the quantity, of one notion of the quantity that I'm going to talk about, is sort of one of the most pervasive objects in classical computer science. So here it is related to things like separation of complexity classes, communication complexity, or de-randomization. But in physics, even quantum complexity, or the notion of complexity that I'm going to talk about, makes sort of surprise appearances, like in the definition of topological phases of matter. So for example, in this very workshop earlier this week, Chinmay Nirkal gave a talk about precisely this and about the relation to quantum circuit complexity. And perhaps most important, at least for the motivation for the results in this talk, is an application in the ADS-CFT correspondence, where circuit complexity is conjectured to correspond to quantities in black holes, like volumes of regions in black holes beyond the event horizon. So I said complexity a lot, and maybe now is a good time to specify exactly what I mean by circuit complexity. So every unitary, I think this is sort of a folklore result, can be implemented using something like 4 to the n many 2 local gates. And it can be exactly implemented like this. And the circuit complexity is then simply the minimal number of such gates that you need to decompose a unitary. And there's 2 things that I would like to point out early on, which is I'm going to talk about unitaries the entire time, but everything in this talk can be defined and proven also for states. So this is not restricted to unitaries. I think it's just easier to stick to one of the results. And the other one is this picture here. It shows nearest neighbor gates, but in the circuit complexity, I also allow for non-geometric decompositions, like a gate acting on the first qubit and the 17th qubit or something like this. So this notion of complexity, similar to the classical notion of complexity, is notoriously hard to feel or estimate or even to bound. The classical case, here I already said it's related to the separation of complexity classes, so it's not very surprising that it's actually extremely difficult to make progress for explicit Boolean functions, and something very similar can be expected for specific states or unitaries. But then if it's so super hard to feel or estimate this quantity, then what is this talk going to be about? And the answer is, it's going to be about generic properties of complexity or generic behavior of complexity. So the question that I would like to ask is complexity, for example, something extremely exotic that we would only expect to see rarely, or if it's in a fine-tuned system, or is it something that's extremely generic and we should expect to see it all around us all the time? And then if you have an interactive system, a typical one, not a specific one, then what's the sort of behavior that we can expect from complexity for most of these? And luckily, there's already a conjecture in the literature, and it's by Brown and Susskind, Adam Brown and Leonard Susskind. And what they conjectured is that in a typical locally interacting system, what you can expect is the following. The circuit complexity should grow at a linear rate until it saturates after an exponentially long time. And this is motivated by various things, but so for one reason, we know that this definitely holds in this very early regime because of growth of entanglement and circuit lower bounds that can be deduced from this. So the emphasis here is on the exponential times, that this holds until exponential times and then it saturates. So before I talk about why I believe that this is true and why people in general believe this is true, let me specify what I mean by typical local dynamics, because there's various things that can be meant by this. And here we have a specific model in mind. And I would like to point out early that, for example, suggesting that proving things for this model should be easier than in other cases was, for example, pointed out in this paper by Brandao, Chemisani, Hunter, Jones, King, and Preskel. And I really like to point out this paper because it got me interested in the question, at least. And it also proves some beautiful complementary results, but I'm coming to that later. So here's the model that we have in mind, and it's called random quantum circuits. And here we previously fixed some way of arranging the gates. First, it doesn't matter, or any possible fixed arrangement would be possible. And then each of the gates is drawn uniformly from the unitary group or the special unitary group on two qubits. And I say uniformly, and here in the slide I use a very fancy word, which is the Haar measure. But if you don't know what this means, it is really it is the generalization really of drawing uniformly from an interval. So there are some specific architectures that we should have in mind. So for example, there's the so-called brickwork architecture. That's called like this because it looks like brickwork. And then we could also, for example, define something that's called a staircase. And there's something that I would like to introduce now, because now is as good a time as any. And it's these light cones that are drawn into this diagram. So later on, I'm going to need the notion of a complete light cone. And that just means that we have some qubit. It doesn't matter which qubit. We just need the existence of a qubit. And then we want paths that go sort of backwards in time and visit every qubit. So this is what I mean when I say a complete backwards light cone. So now that we know what kind of model we are talking about, which is, by the way, it is a time dependent model. So we throw time dependence out of the window, and in return, we get a very nice model where we can prove things. So why do we believe that this is true here? Well, the first reason is really the unitary group is a vast space, at least for the linear growth part. This is the unitary group has 4 to the n many parameters, and we can expect that very few circuits actually cancel each other out, very few arrangements of gates. So the set of unitaries that we can generate using circuits that become longer and longer sort of becomes bigger and bigger, and we would expect that the complexity keeps growing with this. Also, the maximal complexity, there's a natural upper bound, which is just the number of gates in the circuit. And we simply expect that the rate of growth is just the same as the maximal possible rate. Then something that I already mentioned is at very early times, you can prove that, or you can show that entanglement grows linearly. And with entanglement, you also get lower bounds on the circuit complexity. So the idea here would be that if you think about it, entanglement is sort of a phenomenon that measures how far is your state from a product state. And while notions of entropy apparently saturate after a polynomially long time, complexity could keep growing and simply measure how far away are these states from a product state, because this is really what complexity is, right? It measures the number of 2 local gates that you need to apply to your state or to your unitary to bring it into something that's product-like. And then a point which is really at the core of the motivation of Brown and Susskind, which is this wormhole growth paradox that I mentioned before. In this dictionary that is the ADS-CFT correspondence, you have on the one hand the volume of wormholes, and on the other hand you have something in a quantum theory. But the problem seems to be that the volume of black holes seems to grow at a steady rate for an exponentially long time, but observables, local observables in quantum theories tend to thermalize very quickly. And the conjecture is therefore that on the quantum side, we don't have a local observable, but instead something that depends globally on the state. And this is conjectured to be the complexity. So this was the linear growth part, but and it's actually the more speculative part, because the other one is just a saturation. And this is not very surprising in the end. Because we know, I already said this, that every unitary can be implemented using 4 to the n many gates, something that scales like this. So we know that the circuit complexity cannot keep growing after a time that scales like 4 to the n. And also, we know that most unitaries are in fact extremely complex. So once we've hit this threshold that we can implement basically every unitary, the probability of hitting one of these very low complexity unitaries becomes extremely low. And this is also something that I would call a folklore result. And there are various proofs for various different notions of complexity. But in our case, there's a particularly simple argument, and it really fits into this line. Well, I said it's a gigantic group. It has 4 to the n many parameters. But the number of parameters in a random quantum circuit, or in any circuit with R gates, is upper bounded by the number of gates and the dimension of the unitary group on 4 qubits, which is 15, or at least for the special unitary group. So we know that this should generate some set of unitaries, which we believe to be lower dimensional than the entire unitary group, and therefore it should be of measure 0. And the entire idea behind our project is really actually extremely simple. It's just, well, can this latter argument be refined to also encompass the situation where we not compare all unitaries to the set of unitaries generated by some circuit with R gates, but to compare 2 different circuits, namely one with a linear number of gates and one with fewer gates. And so therefore also prove this linear growth part. And this is what we get. We actually can do this and prove the following theory. So this is why I said we need light cones, because here the lower bound depends linearly on the number of disjoint backward light cones that I can fit into my architecture. And I'm going to give you an example soon of how this bound looks like in sort of a prototypical example. So if we have a random quantum circuit in some architecture, and again, T is the number of backward light cones that I can somehow fit into the circuit, then this immediately gives me a lower bound on the circuit complexity that scales like T divided by 9 minus n over 3. And also, I want to say earlier on, you shouldn't worry about this n over 3. It's just an artifact of pushing the scaling down to 9 instead of 15. It doesn't really matter, especially in the regions that we care about, which is exponentially large gate counts. And this bound, it holds with probability 1, and actually not just for exponentially long time, but in fact, until we've hit this dimension threshold. So I think the most interesting example is probably just the brickwork circuits. And here it looks like this. We can fit a backwards light cone into every n squared gates, basically. So the number of gates divided by n squared divided by 9 gives us this lower bound on the circuit complexity in the brickwork architecture. So there's another thing that I find quite remarkable, which is that we can prove this for many different architectures. And in fact, we can show, and we do this in our paper, we show that this holds for most architectures. So if you not only draw, if you not only pick a fixed architecture, but you draw the position of the gates at random as well, then for most architectures, you get a linear lower bound with an inverse polynomial scaling. Right, so for the rest of the talk, I'm trying to be ambitious, and I would like to give you a more or less complete overview of how we prove this, because modulo some boring details, it's actually a very simple proof. And I said I want to compare dimensions of different sets of unitaries generated in different architectures. And for this, I need to view the set of unitaries as the image of a smooth map. Well, the smooth map, it takes as input a set of gates. This is an element of SU4 to the R, and then it just contracts these gates along this previously fixed architecture. And this generates some set in the space of all unitaries. And you see, for example, a visualization of this set here. And obviously we cannot really visualize them because these are extremely high dimensional sets. But you already see a property of the sets in this image that's going to be crucial for what we want to prove. Namely, you see sort of a tube and you see spheres, which is just a collection of manifolds that are sort of stitched together. And in fact, I want to talk about comparing dimensions. So I need to have a rigorous notion of what a dimension actually is from one of these sets of unitaries that are generated by quantum circuits in a given architecture. And it turns out that there's an extremely satisfying answer, at least for me. Unfortunately, these are not manifolds, but they are the next best thing. So there's something that's called the Tarski-Seidenberg principle. And it tells us that if we have a polynomial map, then the image is going to be semi-algebraic. What the semi-algebraic means, it's a very complicated sounding term, but in fact, it just means that you have the set of solutions to some polynomial equations and inequalities. And I want to give you like a very simple example, something that is the set of solutions to a polynomial equation. A prototypical example of this would be sort of the sphere. It's x squared plus y squared plus z squared equals 1. And then you can apply a map to this that's entries are polynomial in this space. And this the map that I want to think about is sort of the projection into the xy plane. And this gives us something that's not a manifold anymore. Well, in this example, it's a manifold with boundary, but this doesn't generalize. But in fact, it can be decomposed into two manifolds, namely is a one-dimensional boundary and a two-dimensional sphere. And this is one of the properties that we want to use, namely that this can always be decomposed like this. And in fact, we get a highest dimension, and then we can just say, oh, well, this is a good definition for the dimension. And also, I should say, we didn't come up with this definition. It existed before, obviously. So now we want to use this notion of dimension to actually compare things. And the following lemma, really, you would think that it's not very surprising. And in fact, we weren't surprised by this because, you know, if you have a sphere and a point, then the probability is 0. But the problem here is that we have sort of an implicitly defined probability measure on this set U of A, which is we actually draw the gates at random uniformly, and then we contract. So if you want to have the probability of a set in this U of A set, then you have to take the pre-image under this contraction map. So it's not immediately obvious that it works, but it does work, and we just have to figure out some details to show that everything works as we expect. So what do we prove? We can show that if you have an architecture A prime and it generates a set U of A, which is of strictly lower dimension than for A, and if we draw at random from the architecture A unitary, then the probability of hitting any unitary that can be decomposed in the architecture A prime is of probability 0. So what does that mean? That means, first of all, that every unitary that has a given circuit complexity, it falls into one of these architectures with a low gate count. And for each of these architectures, we actually have a linearly upper bounded number of dimensions. This is basically the argument that I gave before, that if you have any architecture, then it can be upper bounded the dimension by the number of gates, or something that scales like the number of gates. So if we now want, yeah?
Quick question, can you run this what U of A, what that is?
Oh, sorry, I haven't said. So I meant, wait. I meant to define U of A as the image of the smooth map for a given architecture. So I was just too quick with the slides. So if you have a fixed architecture, then the set of all unitaries that you can possibly get from contracting gates in this architecture is the set F of A. Does that clarify?
And what do you mean by contraction? Do you mean just multiple?
Simply applying the gates, like taking the tensor product, right, and then multiplying the unitaries.
I see.
Yeah, it's really So it's really just a standard thing that you do in quantum computing.
And this is a polynomial map.
This is a polynomial map because in each matrix, taking the tensor product with the identity is a polynomial map. Matrix matrix multiplication is a polynomial map. And also something that I haven't said before, the unitary group is an algebraic set because it is just a set of matrices that satisfies the equation U times U dagger equals the identity. And if you want special unitaries, then you just need to have the additional polynomial equation determinant of U equals 1. So this all actually works out. Okay. So if this clarifies the question, then what I wanted to point out is that actually.
So this is just new to me. So I should be thinking about the variables as being the coefficients in the individual little unitaries. Is that right? As I'm trying to understand the underlying dimension. Sorry, not dimensions, but just variables in the space. It's just the entries of the unitaries to begin with. Is that right?
Yeah, exactly. Yeah, we think about it as we sort of embed matrices in R to the n times n, and then also we don't take the complex numbers, but actually the real numbers in the complex numbers. So it's 2 times n times n.
Okay. And so this is some complicated manifold, and
yeah, the point is it's unfortunately not a manifold, but it is some complicated object that we really don't understand. And the lucky thing is for this restricted notion of complexity, this exact implementation complexity, it turns out that we don't need to understand much about the set except its dimension. And this is basically the entire point.
Sorry, and then just remind me the dimension of this. How do I, if I just had a structure, or the dimension is.
Right. The point is that we can show, like invoking this old result, we can show that it actually decomposes into manifolds. So it is not a manifold, but it's next, like for all practical purposes, it is manifold, right? You can see it as sort of a collection, a weird collection or manifold with corners and like intersected by strings or whatever.
So I should just, if I was crawling around in this space, I just want to find this place where I have most movement, and that's my dimension.
That's the point, exactly. You just take the biggest, in terms of dimension, you just take the biggest space. So what I try to point out is that, well, we have a linear upper bound on the set of gates with a given circuit complexity. And now this lemma tells us that now we just need to find a lower bound on the set, on the dimension U of A for a circuit architecture for which we want to prove linear growth, like the brickwork architecture. So think of the brickwork architecture for A, and for the brickwork architecture, we want to prove lower bounds. And now we need to find a lower bound on the dimension of the set of unitaries generated in the brickwork architecture, for example. So it all sounds very complicated, this U of A and these complicated sets, but I promise you that we have gained something. We have taken this mythological creature that is the circuit complexity, and that definitely requires Herculean strength to struggle with, and we replaced it by something that's extremely well behaved. And we did this by not considering particular unitaries, but instead finding sort of a proxy quantity that can only be assigned to the set of all unitaries that are contracted in a given architecture. And I would like to argue why I believe that this can be represented by a kitten. And it's basically this point. The dimension of U of A is just the maximal rank of F of A. I'm going to explain soon what I mean by rank, but maybe some of you already know this notion, for example, from like analysis classes, for higher dimensional analysis classes. So the dimension is the maximal rank, and the rank is defined for each point. And this means that we can find a lower bound by finding a single point that has a high rank, because by definition of maximal rank, it really lower bounds the maximal rank, and therefore it lower bounds the dimension. And so the thing that we need to do in the rest of the talk is really just find a single point that generates a lot of number of parameters, right? Where taking the contraction and small perturbations, you get a lot of unitaries from these perturbations. And more formally, this is just the rank of the so-called Jacobian, and the Jacobian is just this matrix in some parameterization of F of A meaning the contraction map, where the columns are just the partial derivatives of this map. So how does this look like in our case? In our case, it has a very pretty picture, I think, these partial derivatives. Partial derivatives you get from taking the derivative in some parameterization, and in particular, you could also view them as the first term in the Taylor expansion if you have like an infinitesimal perturbation or some infinitesimal rotation in our case. And for some infinitesimally small unitary, or I should say something that's infinitesimally close to the identity, these can be uniquely parameterized or written as the exponential of Pauli matrices. Pauli matrices being tensor products of X, Y, Z and the identity. So these are the parameters locally that we want to take the partial derivatives of, and we want eventually we want to see that these span a high dimensional space, because then we have in a fixed point a high rank or a linearly lower bounded rank, and because this lower bounds the maximal rank, it lower bounds the dimension, and we are all happy and have a linear lower bound. And these partial derivatives, in this case, they really look like simply inserting a Pauli matrix or two-letter Pauli word after gates. So the rest of the talk is just a very simple combinatorial problem where you just have to find a lower bound on the number of different Pauli operators that you can generate by inserting Pauli operators into a circuit. And I should say, usually if you insert Pauli operators into a circuit, the outcome, if you, for example, commute these through the circuit, you get something that's Hermitian, but you don't get a Pauli operator. And since we only need some specific example, it's easiest if we pick something that we can easily work with, because comparing Pauli operators is easy. They are an orthonormal basis of the Hermitian matrices. And if you have n different Pauli operators, then you have an n-dimensional space. So here we pick just the unitaries such that conjugating Pauli operators by these unitaries, they give us Pauli operators again. And there's a group that's defined by this, and it's simply the Clifford group. So that's basically the definition of the Clifford group. Conjugating Paulis by them gives you Paulis. And in this case, for example, to commute this to the right, you would have to conjugate this Pauli operator by these two gates here. And this would give us a four-letter Pauli operator. And so for the rest of the talk, which is just basically this slide, essentially, we want to actually construct a given set of, for a given architecture that has enough backward light cones. I want to construct a specific point, namely a specific configuration of gates, such that by inserting Pauli operators after the gates, we can generate a lot of different independent Pauli operators. And for this, you have to believe me something technical first, which is, if I give you an arbitrary Pauli string and any backwards light cone, complete backwards light cone, then I can always pick these gates as Clifford gates, such that commuting this entire Pauli operator through the circuit gives me a single qubit Z operator. And because we wanted to do this in full generality, if you look it up in our paper, it looks very complicated, but hopefully this picture already convinces you that we can always do this. Because the point is that the Clifford group actually maps all non-trivial Pauli operators, meaning non-identity Pauli operators, to all non-trivial Pauli operators. So for each pair of Pauli operators, I can find a Clifford unitary that by commuting one of them, I get the other Pauli operator. And we can do this on two Pauli operators whenever we have a gate in front of them. So we could, for example, pick this gate such that conjugating these two gives us the identity Z. If these two are non-trivial, or if one of these is non-trivial, and if not, then we simply pick the identity gate. And we can keep doing this until we hit the Pauli Z operator, and because we only leave identity operators behind, we know that's a single qubit Z operator. But this single qubit Z operator, it was inserted into the circuit after a gate, right? And so it's one of these partial derivatives that I talked about before. So basically what we have just shown is I can take for any Pauli operator a backwards light cone, or a circuit that has a complete backwards light cone, and choose the gates such that now this entire Pauli operator times the circuit is one of these partial derivatives. Well, and we can simply use this to now inductively construct the circuit. Assume we already have, oh, sorry, I used a word here that I didn't want to use. Assume we already had like T prime many backward light cones. And like this, we already constructed a lot of Pauli operators by commuting them through the circuit such that these are all independent. So these are all different Pauli operators. And I have T prime of them, many of them. So what I can do next is I simply pick any Pauli operator that's not in this set. And I can always do this unless we've hit this 4 to the n-1 threshold, because that's the number of non-trivial Pauli operators. And then I can choose the next backwards light cone such that now this new Pauli operator is in the set of derivatives. And it means by appending this, this backwards light cone to the previous circuit, I have increased the rank of this point by 1, and therefore we have a linear lower bound in terms of the number of backward light cones. And this is already the entire proof, basically. This is already how we prove it, modulo some of these differential topology details to make it completely rigorous. So what have we achieved? I think we have achieved something that's like a minimal version, and with a capital M, I should say, a minimal version of what was conjectured by Brown and Susskind. And there's a lot of room for improvement. The first part that I would like to improve is the notion of complexity that we use. In particular, we used a completely exact notion of circuit complexity. And I think in any real world scenario, you would allow for a small implementation error. So I actually would like to show something that the circuit complexity of approximating a unitary up to some reasonable error grows linearly with time until it saturates after an exponentially long time. And we have a partial result, but I warn you, it's really underwhelming. So we can't show exactly this with a probability arbitrarily close to 1. But the error is uncontrollably small. Right now, I don't know how this error scales with the system size, and we definitely believe it to behave. But as far as we know, it could scale like inverse triple exponential or something like this. Fortunately for us, we kind of know what we might have to understand, even though it will be very difficult, certainly. And it is related to the question of how curved these spaces are, because making this robust corresponds to sort of taking a thickened version of these sets and see how the volume behaves. And seeing how this scales with the system size depends on the curvature of these spaces. Then another approach, which is completely orthogonal, I think, is to use T-designs, unitary T-designs, meaning probability distributions on the unitary group that mimic the Haar measure up to Tth moments. If you could show that random quantum circuits generate T-designs, unitary T-designs in a depth that's linear in n and t, then you could show something even stronger, namely that you cannot even distinguish these circuits using measurements with a low complexity from the most useless quantum channel, namely the quantum channel that sends every state to the maximally mixed state. This was established, this connection was established here in this paper by Brandao, Chemisani, Hunter, Jones, King, and Preskill. And they also use it or use previous results on unitary designs to actually show that this notion of complexity also grows even though it's a sublinear growth. Also, I should say it is linear in the limit of large local dimensions. So this was the first part, this was the error tolerance. Then something else that comes to mind is obviously that we've chosen a very particular simple model of local unitary dynamics. And of course, we could also think about, for example, ensembles of time-independent Hamiltonians, or even something that's called the thermophile double state, which plays a big role in this wormhole growth paradox. And here, there's a lot of evidence, most of which based on computational complexity assumptions. So there's a lot of really cool work that was done here. But proving this unconditionally, I at least, I have no angle of attack, even for ensembles of Hamiltonians, because we make crucial use, at least our approach doesn't work because we make crucial use of the fact that we keep adding new degrees of freedom as we add gates. So I think I would stop here, and we still have lots of time for questions if there is any question.
I have one question. So from the beginning, you're looking at this in terms of 2 cubic gates. Would it also make sense to look at this in terms of T-gate complexity?
You mean T-local or something like this?
So like T-gates in the sense of like if you're doing fault tolerant simulation, the 2 cubic gates aren't what's characterizing the complexity, but rather the number of non-Clifford gates.
Sorry, I'm not sure I caught this. So I understood like taking, for example, 3 local gates or something like this.
Like if we have a Clifford, the set Clifford, so we have Clifford gates, and then we consider the non-Clifford gates, just the T gates. These are
T gates. Okay, sorry. Yes. So sorry. Yeah, I got it now. The idea, it doesn't work here because this is a discrete gate set. So the problem is that we keep comparing dimensions, and if we, for example, define circuit complexity in terms of any gate set that is discrete, then it has probability 0 always. So it gives you a statement, but it gives you sort of a nonsensical statement. So we have to make crucial use of the fact that we actually we generate higher dimensional unitaries. So unfortunately, in this case, the approach doesn't work.
Seems like your argument only relied on Clifford gates, if I understood that correctly. So,
yes.
I mean, does your lower bound, when restricted to Clifford circuits, also your lower bound still holds, right? Or does it really rely on the Haar random?
It really does rely on Haar randomness. So this is really, this entire approach is based on using continuous gates or continuous spaces of gates. And once we hit something that's discrete, the entire approach doesn't work anymore. And this is also why it doesn't work, for example, for something classical. Because there you always have some discrete sets of gates. But you're right, the technique depends on Clifford circuits, but we basically chose Clifford circuits for convenience because we only wanted to have some point that generates a high rank, and it turned out to be very easy to work with Clifford unitaries. But actually, there's no reason to believe that it's maximized in Clifford circuits, the dimension. So actually, feel welcome to try to find other points, because once you find a single point that has a better lower bound on the dimension, you immediately improve our results. So for example, it might be possible to even get rid of this inverse linear or inverse polynomial scaling. It's just that you need to find better examples. I have some ideas for candidates. If anyone's interested, drop me a message. But so far, I can't get better bounds.
Sorry, to follow up on that. So if I'm thinking of this thing as a union of manifolds, what that proof said was somehow if you take a point that actually is is it a Pauli or a Clifford or something, from that point, there are points that are maximal in the dimension, right? That the center is that a Clifford circuit. Is that right? You sort of, yeah.
So basically, yeah, I take a Clifford circuit, and then basically the idea is, well, if I perturb this Clifford circuit between sort of global Clifford unitaries, then does that generate many different directions in the unitary group? And the idea is yes, and probably, I mean, it's very much related to the fact that Cliffords plus anything else is universal. And in fact, it was, the idea comes sort of from something earlier where we showed that if you have random Clifford unitaries and then something else, then you also get T designs, at least for low values of T. So yeah, we just constructed some example. We found this construction and it works, but yeah, please find a better example.
And sorry, just a very vague question, which was sort of the whole setup was motivated by, I guess in my mind, it sort of was something about that this is very natural to think of Haar measure generated, locally generated circuits as sort of like the whole framework for things.
Yeah.
Can you say why? Is there anything you could say about why that seems like the right, like that's what we care about somehow?
Well, okay. I mean, to some degree, it is definitely motivated by the fact that every local dynamics can be by trotterization sort of made into this form. On the other hand, it's sort of a minimal example. At least that's also something I tried to convey, that we sort of try to prove a minimal version, and it's definitely to some degree a toy model. Because if you, for example, take a time-independent Hamiltonian, then you don't get new randomness every time you apply a gate. So it's sort of the simplest example that I can think of, at least, that has some locality to it.
Yeah. And so
That's I mean, the honest answer is really, it's Nick called it a tactical retreat. It's the simplest model that I can think of that captures locality.
great, thank you.
Could you say a bit more quantitatively about what approximate version of this you think is expected? Like, what's the notion of approximation and what's the regime of error in that notion?
That's a very good question. I mean, the answer is probably that I simply don't know. I think approximation up to some relative error where the error is fixed should also grow. It's like, say, it's like everything up to something like 1 plus epsilon as a relative error. I would still expect everything to grow linearly. But the question is, does it grow until you hit 4 to the n minus 1? Because this 4 to the n, it's definitely maximal, but it comes from this dimension approach, right? And so it might be that they keep growing linearly or almost linearly, but not until 4 to the n, but they sort of saturate earlier. This is something I could imagine. And I could imagine that this region, when it saturates earlier, that this definitely depends on the error and on the notion of error that you choose. But I would expect it to grow for a long time, probably linearly, simply because I believe that this can be proven. I can't prove it. I thought about it for a long time, and this would certainly be the strongest notion of approximation that I can think of. So not proving that it is actually some implementation circuit complexity, but upper bounding the number of gates that you need for a measurement that distinguishes your unitary from the completely depolarizing channel.
So what part of this current proof is sensitive to error? I guess your result holds with probability 1, so.
Yeah, so the problem is if you allow for any implementation error, essentially, the sets of unitaries generated, or the sets of unitaries that are close to this, are immediately of full dimension, are immediately 4 to the n dimensional sets. So any comparison of dimension immediately fails. So it's the very notion of comparing dimensions that doesn't work anymore. Does that make sense, right? Because if I want to allow for some robustness, I don't care anymore whether you hit these unitaries exactly, but you have to allow for sort of a thickened region, every point that's close. And if you allow this tubular region around your set, then you get something that's not lower dimensional anymore. So I can't compare dimensions at all. Basically, I don't get an upper bound on the dimension anymore. That fails.
Well, I think it's time to move on to the next talk. So thank you very much, Jonas. So next up, I think we should have David Gossett.